So think about the fact that we're trying to pull these electrons sideways. So something that's happening microscopically is that these electrons are actually zooming around, having collisions with other electrons and other ions. So there's kind of a resistive force, right? If you're in a crowded room and you're trying to run in a straight line, you're going to have to slow down a little bit because you're either hitting people or going around them or in some way interacting with them. So similarly, our electrons are experiencing basically a resistive force due to the presence of other particles. You can think of this as kind of being like friction. This is, in a sense, a dissipative force, taking energy away through all of these interactions. Now, why this is helpful to think about is that if I have a book on a table, as this picture shows, and I want to push the book with a constant speed, I actually have to keep applying a force. Now, Newton's law, of course, tells us that a constant speed would result from zero net force. But since there's friction, I must balance that friction, cancel that friction with an applied force. Similarly here, because there is a resistive force, or here it says retarding force, just a force that is opposing the motion, again due to collisions with the ions and other electrons, there actually has to be some sort of pushing force. There has to be a force pushing those electrons forward so that they continue to travel at a constant speed. So do keep in mind that this just means that there's a zero net force because there's that force due to the collisions. So what is going to cause this forward force that causes our C electrons to actually have a drift velocity in that direction? Well, an electric field. And something to remember is that if your force is pushing to the right, your pushing force is to the right, and these are electrons, so your charge is less than zero, right? It's negative. Q in the case of an electron is negative E. That means that your electric field must be pushing to the left. So just keep in mind that that's coming from force equals QE. So if your Q is negative, your force and your electric field are in opposite directions. So we have some sort of electric field in our wire that is causing our electrons to drift in a direction at a constant speed, and we have to have that force there or else they would be just slowed down and stopped by all of those collisions. So you should pause right now, and there's something really important here. We have an electric field in our wire, right? We have an electric field in our wire. Our wire is a conductor. We are not in electrostatics. We are talking about charges moving, which means that we are not in electrostatics. We do have electric fields within our wire. So once upon a time, we said that if you have charges in a wire, they're all stationary, you have no electric field. That was electrostatics. That's not where we are anymore. So that's important to remember. But in this model, we haven't yet said what is actually causing this electric field. Now, if you've been paying attention so far in class, you might look at this picture and say, well, that looks like a uniform electric field. I bet it's a parallel plate capacitor. And I would be very happy because you're right that parallel plate capacitors cause uniform electric fields, but you don't actually put wires in between a parallel plate capacitor, do you? So we need to think about what's causing this actually a little bit differently. It does relate to everything we've been studying up till now, but let's go through this a little bit slowly so you see where this is coming from. So first, let's think about rings of charge, or you can think of this as rings of surface charge density. Now note that obviously this needs to be three-dimensional. We're kind of trying to do a side view. Three-dimensional drawing's hard, so try to understand what I'm attempting to show you two-dimensionally. Let's imagine an axis that is going through the center of these, right? So this is the central axis. And now imagine a point that is halfway between these. So this distance here, this distance to say the center of the ring there, is the same. So there's symmetry. Now we've looked at how to calculate the electric field from a ring of charge as a function of z. So if I first think about this ring, I say that at this point I'm going to have an electric field that way, right? There's some electric field strength from these positive charges right on the axis. It points exactly to the right. But now think about ring 2. If I'm at this point, This ring is equidistant on the other side, and the surface charge density is the same, right? So you can think about this as a linear charge density. Here we're talking about as a surface charge density. So these are the same. That means that my electric field here is that way, E2, opposite. So we would say that the magnitude of E2 is equal to the magnitude of E1. So what is my net E here? So E net is at this very center point is equal to 0. They cancel. So if you are exactly halfway between two rings of equal surface charge density, there is no electric field on you. So hopefully you follow so far. This is just using what we learned in a previous chapter to think about electric fields from extended charge distributions. But now let's look at this next picture over here. Again, we're going to go to the center point, and we're again going to think about these rings of charge. So now, and I'm going to give these a different number just so we can keep track of them as different. We have surface charge density 3 and surface charge density 4. Well, notice that this one has fewer charges. So we would say here that my surface charge density 3 is greater than surface charge density 4. So when I think about my electric field, I again have a field in this direction from 3, pointing to the right. We're right on the axis. But then when I think about the field that 4 is creating, that's going to be smaller. Why is it smaller? Well, the surface charge is less. So what that means is that I end up with a net electric field that is pointing to the right. And you can think about that as it is pointing from the area of greater charge towards the area of less charge. So even though both of these are positive, I have more positive charges to the right, so I do have a net electric field which is pointing away from the area of greater positive charge. So the point of this is that when you have unequal surface charge, different surface charge densities, you do in fact get net electric fields. We're now going to apply that to understand where our currents come from. If I have a wire, for instance, a wire that is connecting a positive electrode of a parallel plate capacitor and a negative electrode of a parallel plate capacitor, in some regions I have a more positive surface charge density, and in other regions I have a more negative surface charge density. And we'll look at a different picture that looks at this in a little more detail. But note that this means I actually have a varying surface charge density along the wire. And this situation here is what we immediately just talked about on the previous slide, that we have very positive and we have less positive, and that results in electric field to the right. Over here, we have a little bit negative and more negative. That also results in an electric field to the right. If you're in between some positive and some negative, well, very obviously, that creates an electric field to the right. So you see that in this scenario, the varying surface charge densities will naturally give us an electric field throughout the wire. Now, we're not rigorously proving that this is a uniform electric field. However, that is going to be the model that we're thinking about. So we're quickly going to be switching to talking about potential difference in current and not talking about electric field after that point. But for right now, we are effectively assuming that this is a uniform electric field throughout the wire, which is a simplification, but will help us understand what's going on.